Okay, sorry, ich war noch gemutet. Sag nochmal.
Ich kann auch nochmal sagen, den Standardtest. Kann auch nochmal sagen. Ja, super.
Ja.
Klingt gut. Dann legen wir gleich los. Ne? Okay, good. So today we continue with lattice trapdoors. Last time we saw that we already mentioned that we have two types of lattice trapdoors: short basis trapdoors and so-called gadget-based trapdoors. We talked about a little bit about the short basis trapdoors. And the point that I want to mention again is that we want short bases for typically lattices of this type, lambda perp of A, and we usually cannot generate trapdoors for all matrices, but for almost all matrices. And in fact, the way we generate these things is not that we first generate the lattice and then a basis, but we do this concurrently. But what we want is that the way we generate these things is almost uniformly at random. The reason for that uniformly at random is that the matrices A will be keys, public keys usually, for later on in crypto systems, and there we need a good distribution, mostly the uniform distribution. Okay, so and that will be the case also for the gadget-based trapdoors that we talked about today. Short bases, as I said, they can easily be used to solve SIS. Actually, it is a solution to SIS. It's also leads to efficiently computable solution for ISIS, the inhomogeneous version. And as we saw last time, it also, did I already mention that? Yes. So it also leads to our algorithms to solve search LWE. Okay. And so today we want to talk about gadget-based trapdoors, which can only actually be defined for these lattices lambda perp of A, basically, but that's good enough for our cryptographic constructions. They turn out to lead to somewhat better parameters, and they lead to something that they are much more powerful than short basis trapdoors. They can be used in many more cryptographic constructions, as we will see in the seminar. And the way, so let me just briefly recall how we define these things roughly. So we first define gadget matrices for which we can solve SIS and LWE easily, actually ISIS. And then we'll show how to hide these gadget matrices in general, basically general matrices, and have the trapdoor then can unhide the gadget. We'll see exactly what that means, what this unhiding means. And then we'll show how to construct these for almost uniform matrices again. As the reason why we want almost uniform or uniform matrices, that's the same as before for the short basis. The A's will become public keys or public parameters in certain cryptographic schemes, and those we usually want to be uniform, so that they do not leak or provide much information to adversaries. And we will see that there are lots of parameters involved, but not just as here M, N, and W. There's actually a little bit more involved, but it turns out that these things are not very difficult. They're actually very elegant. Okay, so in the first part, we want to define these gadget matrices. And we'll start with the easiest case, namely n is equal to 1. Okay, so we want to do this, so sort of we want to define G to be a matrix in Z, Q, N, comma, M. So it has just one row. Cryptographically not very interesting, but as we'll see, once we have it for n is equal to 1, we have it for everything, for arbitrary n. And what we do is, so we have our parameter q, which is a natural number, and we set L to be the log of q, rounded up the log to base 2. And then we define the following vector. It consists of all powers of 2 up to power L minus 1, including 0, the 0th power. And this we call the vector G transpose. So when I write G, that's always a column vector. If I say transpose, that's a row vector, as I wrote down here. So that's an element in ZQL. And we'll see that we can, as I said, we can solve ISIS and LWE easily for such a matrix, and the lattice that it defines. It also defines a lattice, lambda perp of G transpose. So it's a matrix, just having just one row, but that doesn't matter. And I will not talk about this today, but next week I'll talk about discrete Gaussians, and then I mentioned that we can also solve this ISIS with solutions distributed according to a certain discrete Gaussian. So we cannot just find a solution, but we can we will have many solutions. But you can easily see that if I have here a row vector, like let's look at ISIS. So that means we look at, with using that terminology, we want to look at x such that this is 0, mod q. Well, but there are many vectors x that satisfy this, right? They are all in the kernel of this thing, and the kernel has dimension m minus 1. So there are q to the m minus 1 many solutions. Because x comes from that q to the m. We just have one equation, and so the kernel is m minus 1 dimensional. L, sorry, this is L. L minus. Yeah. This is T. Yeah. Okay. So it's L minus 1 dimensional. Always remember, dimension of kernel plus dimension of image is dimension of the domain. And so we have many solutions, and we also have many solutions to ISIS. Well, the number of solutions is always the same, no matter what you have, because once you have a single solution, then add an element from the kernel, and you get another solution. And so here we show that we can even generate those things according to a certain distribution. We really generate random solutions according to this Gaussian distribution. And why is that important? I'll mention that again, but we'll talked about this pre-image sampleable functions. And it turns out that these things correspond to these pre-image sampleable functions, and there we have the distributions on domains, and we need this trapdoor to go in the reverse direction, and that's basically what we do here. Okay, so but how do we solve ISIS for this thing? So here is we have our G as above, and we now have a U in ZQ. And what we want to do is we want to find an X in ZL with G times X, T times X is U mod Q, or the inner product of G and X. Sometimes so usually to make sure, when I define the problem, I will say, so the problem here is defined by this U and the G. The problem is defined by elements in ZQ, but I usually talk about solutions in Z with integer coefficient, with integer entries. I could also do it with X and Z LQ. For reasons that have to do with the Gaussian distributions, I prefer to do it this way. Other people do it differently, but I prefer it this way. It's sort of cleaner a little bit. So now how can you actually do this? well, what you want to solve here obviously is, so if x is x0 up to xl minus 1, then G transpose times x is simply, well, what is this? It's xi times 2 to the I from 0 to L minus 1, by definition of my G. Yeah? So if I want this to be U, and U is, because it's in ZQ, it lies between 0 and Q minus 1, and because I defined my L to be the logarithm of Q rounded up, I can take my X simply to be the binary representation of U, the bits of the binary representation. And that's it. The base 2 binary, the representation. That's it. And we all know how to compute that, right? Well, most people know how to do that. And that gives us a vector whose entries are only 0, 1 of length L. Hence, its Euclidean norm is square root of L. And that's it. So we can find the solution always of length square root of L, and that is square root of log Q, okay, roughly. Whereas in general, you would expect, well, you would have that these things are maybe elements from ZQ or between 0 and Q minus 1. But in fact, you can, the way this gadget is defined, you can do it with just zeros and ones. So that's easy. LWE is a little bit harder, but not much. So let's look at LW for this gadget. And for simplicity, I assume that Q is a power of 2, namely 2 to the L. Doing it for general Q is technically just a little bit more involved, but the basic idea is the same. So there's nothing really new that we have to do. So how can we solve that? And fortunately, I don't even have to define this LW. You remember this has this error distribution. I just need a simple condition on the error distribution, and which we'll see in the next line, actually. So to define the problem, we have given G as above, and we have given a vector B transposed, which is G transpose times an S in ZQ and an error vector of length L. And I assume that the error terms are all between minus Q4 and plus Q4. So our error distribution should be such that with high probability errors land in this interval. Okay? All the Gaussian distributions with the right parameters will do that with overwhelming probability. Okay? And then we want to find this S, which is in ZQ. Here I actually want it to be in ZQ. I want it between 0 and Q. Okay? And to do so, I will again write S. I will write S in its base 2 representation, in its binary representation. The SIs are its binary digits. And I will compute S by recovering the binary digits one by one. Yeah. And so the SIs are from 0 to R minus 1, and I also have E, the error vector is from 0 to L minus 1, and B is also from 0 to L minus 1. Just makes more sense because here I really have to start with 0, so it's better to enumerate the entries in a vector starting with 0. Okay. It's just a terminology. Okay, so, and then let's look at this equation. What is this BL minus J? So BL minus J is S. It's the same for all these things. So this vector S gets multiplied by a constant. So every entry gets multiplied by the same constant. So and for BL minus J, the entry in the vector is 2 to the L minus J. Yeah? For some reason that will become in a second, I do it L minus J and not J. And so this entry is this S times 2 to the L minus J, and I add this arrow term, E L minus J, and that we can write down. I use its binary representation. So in everything up here, I add it to the exponent, which here is I add L minus J. Rearrange the summons a little bit. Plus this EL minus J, mod Q. And remember, in our case, Q is 2 to the L. Okay? Now, whenever this part here is positive, or let's say non-negative, then I know that this part here is divisible by 2 to the L. Hence, taking it mod Q, which is 2 to the L, I can just ignore it. Okay? So fixed J, and when is it? So for all i's that are at least J, I have the 2 to the L in there. So all these terms disappear looking at it mod 2 to the L. So all that remains is this term here. I didn't change this here, but I changed the summation index, the upper bound for the summation index, everything from J and for I, at least J and larger disappears. Okay? Now this is the formula that we are going to work with. Okay? And now let's look what we get from this. And we start with J is equal to 1. Okay? J equal to 1, J minus 1 is 0, so there's just one term in here, namely for I being 0. So we now know that BL minus 1 is exactly S, and I can just jump right to this part here, is S0 times 2 to the L minus 1 plus EL minus 1 mod Q. Okay? This term we know. Okay? This guy here is between Q minus Q fourth, is between, just let me write it like this, EL minus 1 is less than Q fourth. This guy here is Q half, right? 2 to the L minus 1, Q is. And this guy here is in 0, 1. Okay? Now what you do is the following. If BL minus 1 is closer to 0 than to Q half, output S0 is 1, otherwise output S0 is 1. Right? And my choice will be correct, because if this here, if S0 is 0, then what I get is between minus Q fourth and Q fourth. But Q fourth not included. The positive one is not included. If, on the other hand, this is 1, I subtract at most. This thing here will lie between Q fourth included and 3/4 of Q. So it's closer to the Q half than to, that's why I picked this here, this part here. This separates 0 and Q half. Okay? Okay? And I always do this modulo Q, and I use the centered, basically, part, right? Because I have minus Q4. Okay? So by this simple check, I can determine S0 with certainty, no error involved. Okay? Now, assuming that I already know S0, it's easy to determine BL minus 2, which is for BL minus 2 mod Q, we have here two terms involved. Yeah? And we have S1 times 2 to the L minus 1 plus S0 times 2 to the L minus 2 plus EL minus 2 mod Q. Right? Yeah. We already know this part, so we can rewrite this as BL minus 2, which is given to us. We know that, minus S0 times 2 to the L minus 1 is equal to S1 times 2 to the L minus 1 plus EL minus 2. But again, we have that EL minus 2 in absolute value is bounded by Q4. More precisely, it lies in this interval, right? And we can do the same, we can use the same condition to determine S1 applied to this term here. Okay? And once you have S0, S1, you go to BL minus 3. You get a similar thing here, whereas you start here with S2 times 2 to the L minus 1, S1 times 2 to the L minus 2, times S0 plus S0 times 2 to the L minus 3. You know S1, S0, subtract, same condition. And so in this way, you go through the bits of S one by one to determine all of them. Yeah? Basically, the running time of this algorithm is order log Q, something like that, or order poly log Q. But it's very efficient. Okay. If Q is not 2 to the L, there's a little bit of dirt involved, and so you have to be a little bit more careful. But still, the idea is roughly the same. Okay. So that's all. This is quite easy. But it's only true for here with n is equal to 1. Okay. Okay. Now we want to generalize it to a matrix that has a general number of rows n. And we'll see the number of columns will also depend in some way on n. So it's not that we can generalize. That's different to what we had in the basis, in the short basis case. Here we will have a certain relation between n and n, that's n and m, that's to some extent stricter than for the short basis trapdoors. But usually in practice, that's not a big deal. So how do you do that? So go to the general n. It's roughly the easiest way you can do that. You basically concatenate these things in separate dimensions. So what you do is for n in n and q, l, and g as above, we define this g to be the tensor product of the n-dimensional identity matrix with g to the d. if you want to do quantum computation, you need to know what tensor product is. Here, it's simply you take a diagonal matrix, and then you place on each diagonal, you place this vector, and you separate these things. So what you do is, here you have GT in the first row, then in the next row, everything here is 0, everything's here 0, you put in GT, and so on. And you do that until the nth row. Okay? In general, if you want to know that, mathematician will hate me for that. What I write down here is, if you have a matrix A, which is Aij, and a matrix B, the tensor product of these things is simply you replace every entry Aij by multiplying the matrix B by Aij, and then you get this huge matrix. Okay? Dimensions multiply. And that's exactly what I did here. So that's the basic computer science definition of a tensor product. Mathematicians, it has a universal property, makes following diagrams commute. Anyway, tensor products are used to replace bilinear maps by linear maps, period. That's what you do. So maybe you should look at bilinear pairings and replace them by tensor products. Anyway, so what are the dimensions of this matrix? Well, we have n rows, yeah? And the number of columns is n times L, because each of these things here is L columns. Okay, so that's it. That's our G. Now we have to make sure that for this G, we can also solve ISIS and LWE. And ISIS, actually in both cases, we basically apply the methods for the one, for n is equal to 1 and do that blockwise. So let's look at it for ISIS. Now we are given a vector u in zq to the n. Okay. Right, because our results, and we want to find a vector x, which is now has in z to the n times L. Because our matrix G has n rows and n times L columns, so x is of length n times L, the result is of length n. Okay. And what we do is we write our u in terms of its coefficient or its coordinates, the ui's, and then for each I, we solve G transpose times xi is equal to ui, where the xi now is an L-dimensional vector. Okay? Because that's, and then we concatenate the xi's to get our x. If you go back here, well, you have here you want this x to be some ui. Well, it's just the first row that matters. Right? And all the other entries down here, they get multiplied by 0 anyway. So they don't matter. So we partition this really into the u, we partition into its coordinates, and then for each coordinate we have a separate block of L coordinates in our solution vectors. If you write down here, so you have this G transpose, you have here G transpose, you have G transpose, and then you can write down here the x1, then you write down here x2, and so on, until at the end you write down the xn, and that gives you a u1 up to un. Right? And since all these things here are 0, 0, 0, 0, 0, for the first coordinate here, only this part here matters. And for the second part, only the second coordinate, only this part matters. So that's why you separate all these things and reserve for each coordinate a block of L coordinates in the solution. Okay. But this gadget is, as you can see, M is here n times L. So there's a relation between n and M. M is a multiple of n. So that's what we get here. What's the length of this vector? Well, again, our solution vectors contain only 0, 1s. They inherit that from our G thing here because we just concatenate the solutions. But now instead of L dimensions, we have n dimensions, so the length is roughly square root n times log Q. And it's a very simple operation, but it turns out to be really, really very powerful. I'll talk a little bit about it later. And therefore, we express this operation in terms of a bit decomposition function, right? Which means that we have, if our domain is zq to the n, and we map that to z to the nl. In fact, we map it to 0, 1 to the nl. What we do is, or in general, we can define that more general. Given a vector u, we map that to a short solution to G times X is U mod Q. The 0, 1 solution that I presented to you is one candidate. Okay. And hence, for all u, we have G to the minus 1 of u times G is u again. Okay. And that actually turns out to be really, really powerful. You can easily see that. So in terms of length of vectors, something really amazing happens here. If you have a vector in this here, right, its length in general, so u is in zq to the n, then its Euclidean length is bounded by square root n times q, right? That's an upper bound, well, actually q minus 1, never mind. Each entry in the vector is at most of length q minus 1. In the Euclidean lengths, they get squared, and you take the square root, and you get here by the square root of n. Okay? Okay. Now let's look at G to the minus 1 of u and really think of this 0, 1 solution. Okay? Its length is bounded by square root n log q. Okay? Okay, so this is square root n times log q. So, but there is no loss of information. From this guy here, I can recover this guy here by multiplying it with G. But I get all at once, I get much shorter vectors. I have to pay a price. My dimension goes up by log q. Okay, but still, it's short vectors, and usually we are interested in short vectors. So this is something that you can often do. So you'll see that also in some of your papers. You work with these general things. They are too long. You do this operation. You make them short. You get something that makes them again large. You spend even more dimensions, make them short. Yeah, and so on. So that's a very powerful operation. Yep. Sometimes you will even people not use the brackets here as if this was a linear operation, which it is not. Okay. It's a highly nonlinear. It's a really nonlinear operation. Okay, good. So now let's look at the case for LWE. And here it's basically the same thing. We do it in a block by block fashion. So given a B transpose, which is some S transpose times G plus E transpose, where each entry of E is in Z to the NL, and also B is of dimension NL, whereas S is only of dimension N. Okay? Because this G has N rows, NL columns. I multiply this S transpose from the left. So what this does is it computes a combination of the rows. Multiplying with a row vector from the left leads to a combination, linear combination of the rows. Multiplying by a column from the right is a linear combination of the columns. Since this is a linear combination of the rows, it's the results are dimension NL. Yeah? And if you ever look at books on coding theory, they often write things from the right, but treat it as if it's from the left. I don't know why they did it. At some point in the 1960s, probably, they decided this is a good idea to confuse students, so let's stick to it anyway. So now what we do is we write B, which is a vector of dimension NL, as n blocks or n vectors, each of length L. Okay? Well, because our matrix here basically partitions everything into blocks of these things. And S is in ZQ, S is in ZQ to the n, so we write it as n elements in ZQ, and E we can partition in the same way as we partition the B. And then this thing here, this equation here, translates simply to a block by block combination, because down here there is nothing. Right? The combination of rows, so the combination of these rows in the first L coordinates only is the multiplication of this vector here. In the second block of L coordinates is only this one here, and so on until here. Okay? So what we do, we just solve LWE in each of the blocks separately. How do we do that? N is equal to 1. Because this now here is really just a number. Okay? And that's it. Okay. Good. Yep. Just one more remark before I go to how we hide these things in general, more general matrices. You may wonder, so I usually talk about these things here, G, You may wonder whether can we actually concretely write down a basis for this lattice that's short? And the answer is yes. You can easily write down a basis for this lattice here in arbitrary cases. And actually which is a short one. Okay. I won't do that, but so for these things you can easily define a very nice basis. Okay. Okay. Okay, good. Good, then now if there are no questions, we go to this hiding and unhiding part. Let me clear the boards. Actually, for this part, it's mostly irrelevant what this G is. The only thing that we really need about it is that we can solve ISIS LWE efficiently with short solutions. The rest is mostly generic. You could use, if you wanted to, any other G's, but these G's have turned out to be very useful and powerful, in particular because of this G to the -1 and some other nice properties that they have. Okay, so we fix some gadget matrix G in ZQ n times NL. And a trapdoor for a matrix A is any short matrix, short meaning small coefficients, whatever short means. We'll see that later, maybe next time. And R lives in Z to the M times NL, such that A times R is equal to H times G mod Q for some invertible matrix H. I don't care about the precise definition. Usually H is somehow fixed. The identity is a good candidate, but not the only one. Yeah? So that's the relation we want to have. And H is often called the tag for the trapdoor. It has a certain tag. And let's see that all this fits together. So A times R, we can do that only if the number of columns in A is the same as the number of rows in R, which it does because in both cases we have this to be M. Okay. So this product has n rows and NL columns, the same as G. Now H lives in dimension n times n. So if I multiply from the left with a matrix of dimensions n times NL, the resulting matrix is again of dimensions n times NL. So the two things lead to the same dimensions. So just a sanity check. Okay. And okay, so that's a trapdoor. And the quality of such a trapdoor is given by this parameter, which is the maximum length of a vector r times u, where r is of unit length. Okay. This maximum really exists. If you remember analysis, u times length of u is 1 is the surface of an n-dimensional sphere, which is compact. R is continuous. Every continuous function on a compact domain has a maximum and a minimum. Remember it probably. If you have a continuous function defined on an interval, closed interval, it has a maximum. Compact is just a generalization of interval. Continuous is continuous. So this thing is really a maximum. What does that mean? It really measures how much R stretches a vector. Yeah? That you do here, U is 1, you could also instead divide always by the length of U. Okay? And you can always say that, so R U divided by the length of U is the same as the length of R divided to this thing here, because R is linear. And this is a unit vector. So this really, if this is always less than S1 of R, so you can always say that R of U is always less than S1 of R length of U. So this really means how much does it stretch or contract. S1 can also be smaller than 1. Okay? So in general, what happens, here's your ball, and the surface of a ball, and with R, assuming R is full dimensional, whatever, which is not, but never mind, it does map this to an ellipsoid. And an ellipsoid, you may recall, in 2 dimensions you have these 2 main axes. Right? So there is always something that's orthogonal. And this here, that's the length S1. Okay? There's also an S2, which is this here. There's also an S3 in 3 dimensions, which is the next longest one. And these things, S1 is called the largest singular value of matrix R. Singular values are a generalization of eigenvalues. So, as you can see, well, because this is a maximum, there is a vector that attains it, for which R has eigenvalue. Doesn't really make sense because it's not, it need not be quadratic. You have to be careful for that. You have to define left and right singular values and vectors. Never mind. No, you have to find singular values, but right singular vectors and left singular vectors. Okay, anyway, but this is, so this measures how much it stretches it. How much, if we apply R to a vector, how much longer or shorter it gets. Usually we are interested in longer. We find something that's short, we apply R, and then we want to make sure that it doesn't stretch this vector too much, as we'll see. Okay. Good. So anyway, this is how we, so if you multiply R on the right to A, we get H times G. Okay. And once we have a trapdoor for a matrix A with, and we know the tag, then we can solve ISIS for A. And we do that as follows. To find, so now we want to find, given a U in Z Q to the N, assuming it does have a solution X such that A times X is U. We always assume that this exists. As we will see, with high probability over random choice of A, that is true. There always exists one. So to find a short X, what we do is we compute H to the minus 1 times U. This really, H to the minus 1 is a linear map. H is invertible. Here I use that H is invertible. And to that thing, I apply my g to the minus 1 operation. That's my w. And then my x will be r times w. Okay. Now, the output is correct. Why is that? Let's look at it. H times x. X is r times w. So this is I times r times w, which by the trapdoor property, A times r is h times g. Right? So this becomes h times g times w. But now, w, g to the minus 1 times g, that becomes h to the minus 1 times u. And then I'll multiply with h, so that becomes u. I do these operations in the reverse order. At first dup, dup, and then dup, dup. So I get u. Okay. So all you have to do is basically solve this ISIS on this vector. This g to the minus 1 is simply the ISIS solution for the G trapdoor. Right? Yeah. How long is my vector? Now here comes already this nice part about this g minus 1 thing. Okay? U is of arbitrary length. H to the minus 1 is of arbitrary length. But g to the minus 1, bingo, it's short. And if S of 1 of R is a good trapdoor, then this last operation will not increase the length by a lot, namely only by S1 of R. So we know that W is of this size here. That was our condition. And then X is of this size at most. Okay. Or with, there could be small constants involved. They are if Q is not a power of 2, something like that. Yeah? But already here you can see this. So this g minus 1, it computes a short solution no matter what. Or in other words, it turns a vector into something that's short, but has more dimensions. Okay. So that was ISIS, the inhomogeneous short integer solutions. Now let's go to LWE with trapdoors. And here we have A, R, and H as before. G is always fixed. And given now we have B transpose, S transpose times A plus E transpose for some E with small entries, we need to find S. So E again comes from the error distribution, and we assume that the error distribution with high probability produces errors with short entries. Not just short overall, but really short entries. Makes a difference sometimes. And what we do here now is we compute D transpose, which is B transpose times R. B transpose is a row vector, and so we multiply it to the left on R. Then we solve the LWE for D transpose and gadget matrix G to obtain some vector W. And then we output W times H to the minus 1 transpose. So the inverse of H, and then we transpose the matrix. And that's the shorthand notation for it. Or in other words, if you remember it, if you transpose a product, you reverse the order of the product and transpose individually. So if I do that, S transpose, I reverse the order and transpose individually, W transpose H to the minus 1, because the transpose of transpose is the original one. Yeah. Now, does that work? Yeah. what I claim is that the algorithm above outputs correct S if E transpose R has small enough entries. Okay, and remember that for LWE gated matrix, we needed that the entries needed to be between Q minus Q fourth minus Q fourth and plus Q fourth. So if I can guarantee that this guy here has so small entries, then this will work, I claim. Okay? Not the E, but even the entries of E must be a little bit smaller so that even if I stretch them a little bit by R, they still are short or small. Huh? Now, why is that true? So assume we have B transpose is equal to S transpose times A plus E transpose modulo Q, whatever. Now I multiply everything to the right with R. And that is S transpose times A times R plus E transpose times R mod Q. But this here is D transpose. Okay? This here is S transpose times H times G plus E transpose times R. Q, right? Again, A times R is H times G. Okay, now I find a solution which gives me this vector here, which is W. Huh? This here is my W. Okay? But what I want is my S. And then I just multiply with H to the minus. So this gives me my double, and then I multiply by H minus 1. And then you get the whole thing back. And that's it. And if this is short enough, this guy here, then this LWE for my gadget G will work. And I always have this H in there, but it doesn't really matter because it's always invertible. Okay. And you can actually, it's a little bit, to be really, you have to be a little bit more careful because you have to, this is a solution to this. Does that imply that's a solution to this here? That's true if both solutions are unique, which they are. Yeah. It could be that the solution to this doesn't translate to a solution to this one, because with the multiplication with R, I kind of destroy something. But if solutions are unique, that works actually. Okay. But anyway, so this really works. So but you need that this R is nice enough. In the sense of having not too large first largest singular vector. Okay. So good. So yeah, it's all nice, right? Except how do we find such trapdoors, and how do we generate a matrix A with such a trapdoor? Right? This says, well, if I have it, it's nice, but we want to have it. We want to, and the only way to do that is we actually generate it together with A. So we need a certain way of generating A and R together. And we do that in the most straightforward way you can imagine, and sometimes the deep insights are just be bold. Just try something that's obvious. So again, but first let us recapitulate what we want. We want an efficient algorithm that generates A and R, A and the trapdoor R. The distribution on A is close to uniform on ZQ to the n times m. And R is a trapdoor A with tag H, where H is fixed by someone outside. Typically, it's an application or by some entity. Some entity in an application. That's what we want. These two properties is what we want to achieve. And here's the algorithm. First, we choose an A bar uniformly at random from ZQ to the n times M bar, where M bar is a natural number that's smaller than M. I'll tell you a little bit about M bar later. M bar is responsible for part 1, the choice of M bar, also with R bar. Okay, then we choose an R bar with dimensions M bar times NL, where each R bar is chosen according to a discrete Gaussian distribution with small parameters. So it's concentrated around 0. There are several ways to generate these things. This is the one I prefer. Say it's the more powerful one. Okay, so it's Gauss. I talk about Gauss next time, but this here is just no. This is Gauss, and somehow S determines when this becomes extremely flat here. Or I should actually draw this. Right? So that with high probability, all these things are very short. And then I compute and output the following matrix. A consists of A bar concatenated H times G minus A bar times R bar. And that is a matrix it has n rows and m columns, where m is m bar plus n times L. Okay, and my R consists of, I have my R bar matrix, and below that I write the n times L identity matrix. Now let's see that all the dimensions fit together. Okay? And then obviously I will claim that this is a trapdoor for A. Sometimes we just say that our bar is a trapdoor because NL that is fixed. Okay, so so that's but according to my definition, I should say that R is a trapdoor. So what are the definitions? So let's collect, well, we already have this, right? So here, everything I have, because here I concatenate by concatenating the columns. Okay? Concatenating columns doesn't change the number of rows. So everything I have in here should have n rows. Good. A bar has n rows. G has n rows, and H is n times n, so H times G has also n rows. And A bar times R bar, A bar has n rows, R bar doesn't really matter. It just matters that it has the same number of rows as the number of columns of A bar. But it has n rows as well, so we can at least form this part here. Okay? Now let's collect the number of columns. So A had its number of columns is m bar, and then how many columns do we have in here? Well, this guy has n columns, nl columns. This guy here is also nl columns, so I can even subtract the two to also make sense. So from this part, I get m bar columns. From this part, I get nl columns, so this is it. Right? So everything fits together nicely. But I only generate matrices where M is of this type here. M bar we will fix later on the next slide, but M bar will be significantly larger than L, even larger than we need for other reasons anyway. Now let's look why it's a trapdoor. Oops, that's the part I want to write down. Sorry. Multiplying concatenated matrices is like multiplying matrices, where you treat individual things as if they are numbers. Okay? So what we want to do is we need to calculate A times R bar I N L, which is R bar concatenated H G minus R bar times R bar I N L. Okay? Now, this guy here has the same number of columns as R bar has number of rows. So if I multiply these things, then this matrix gets multiplied with this matrix. And this guy here gets multiplied with this. Right? So what we get here is R bar times R, I bar times R bar, plus, it's like vector multiplication, or matrix multiplication, but each entry is a matrix. And here you get this guy times this, so this is H times G minus A bar times R bar, which is H times G. Bingo. It's a trapdoor for this A with tag R. And usually people call this R bar the trapdoor, actually, because this INL is just a constant matrix, obviously. Okay. So part 2 is guaranteed. But we also have to show that it has good quality. Okay? And that is what I do on my last slide, which, so R, or simply R bar is a trapdoor with tag H for A. And what one can show is that if M is large enough, then using the right Gaussian distribution for R, and M bar is something like C times N log Q, where C is slightly above 1. You can even do it slightly, you can actually N times log Q plus some error term, or plus some additional terms that are lower order. Then one can show that the distribution on A is statistically close to uniform. Okay. That actually, so remember, we have many more columns than we have rows. So we concatenate many more vectors than we have dimension of the vectors. So there is a chance that this actually is close to uniform, or that this is not just some fixed value or whatever. Okay? This turns out not to be too difficult to prove. There are other versions of it where R is generated as a plus minus 0 matrix, where you prove it using an extremely important result in cryptography, the leftover hash lemma, which for pseudo-randomness and all kinds of things, and it's very important. But okay, so we have that property. So A is statistically close to uniform. And what can also show, and that goes quite deep into so-called random matrix theory, is that with high probability, if we choose R as defined here roughly, with a certain parameter S, that is roughly the standard deviation, then the largest eigenvalue, this largest singular value of R is S times square root of M bar plus square root of NL, which is upper bounded by S times square root of M. Yeah. You cannot choose S too small because then you will not have this here, but you can choose it relatively small. I will tell you next time what it roughly can be. Okay. Okay. Good. And then we have all we want. Turns out that these trapdoors have many more properties. They can be so-called punctured. This puncturing techniques is something you will see in security proofs. The puncturing is often done to, you have an adversary, you want to reduce it to some other adversary. You have to answer queries. You can, for certain values, answer the queries, but for one thing you cannot answer the queries because it's punctured. At that point something happens, and that's exactly the value that you're interested in the reduction. So it can be extended. It appears in almost all constructions, except for the one I present to you in 2 weeks, where I present to you a signature scheme, lattice-based signature schemes using the random oracle. There you don't need the extension. But then in the talk, in the seminar, we'll see with the standard model, there we already need extensions. And for IBE and all things, we all need extensions. They can be randomized. Also nice. That's often for anonymity of things. And there are many other examples. You can define sort of arithmetic on trapdoors. And that's very useful for homomorphic encryption, homomorphic signatures. And also on sort of, on trapdoors and related things. And what one can also show, and that I will talk a little bit about next time, they can be also used to compute these ISIS solutions distributed according to these discrete Gaussians. Remember ISIS solutions? We saw how to compute a solution, but if we want to do that in combination with pre-image sampleable functions to get good signature schemes, which I will do in 2 weeks, we need that we sample these solutions to ISIS according to a certain distribution. The trapdoors here will allow us to do so. And then we get these pre-image sampleable functions that I talked about 2 weeks ago, I think, or so, where we saw how we can use pre-image sampleable functions to define signature schemes. But there we need like functions computed in one way and in the other way, and for those we have these distributions. And that's it for today. And next time I really talk about discrete Gaussian distributions. Now it's about time that we'll actually define what these things are and what kind of nice properties they have. But I can actually already show you at least a picture, I think. Can I show you a picture? I cannot show you a picture. It's not, for some reason it's not there. Okay. Should be there. It's not there. Okay, anyway, next time we'll see what Gaussians are. But they will be generalizations of the pictures I had on the board at some point. Okay, that's it for today. Questions? Good, then that's it. Thank you. Warum macht ihr das?